All right. Powering movement, the physics of the quadriceps. All right. So today we're going to be exploring one of the most powerful and dynamic muscle groups in the body, the quadriceps. These muscles are essential for pretty much any movement involving your legs, whether that's running, jumping, kicking, or just walking upstairs. In this project, we'll explore their biology and biomechanics, from their structure and function to the physics of how they generate motion. Then, we'll show you how they play a critical role in a key athletic movement, the vertical jump. We'll be diving into concepts like torque, work, moment of inertia, energy transfer, and more. So let's get started. All right, the quadriceps femoris, or quads, are actually four muscles located on the front of the thigh. The first one is the rectus femoris. The rectus femoris is centrally located in the middle of the thigh, running straight down from the hip to the knee. It is unique among the quadriceps muscles, as it is the only one that crosses both the hip joint and the knee joint. The second is the vastus lateralis. Positioned on the outer side of the thigh, the vastus lateralis is the largest and strongest of the quadricep muscles. It plays a significant role in knee extension, providing strength and stability during leg movements. This muscle is heavily engaged in activities that require powerful leg propulsion, such as sprinting, jumping, and cycling. The third is the vastus medialis, and it's located on the inner side of the thigh and is crucial for knee stability in addition to extension. One of its key roles is to help stabilize the patella, or the kneecap, ensuring smooth and controlled movement during bending and straightening of the leg. This muscle is particularly important in preventing knee injuries. And lastly, the last muscle is the vastus intermedius, which is found beneath the rectus femoris, inside the thigh. This muscle, while not as visible as the others, is essential for knee extension and provides structural support to the quadriceps. Due to its deeper positioning, it works in conjunction with the other quadricep muscles to ensure even force distribution during leg movements. Um, and thus, these muscles converge into the quadriceps tendon, which connects the patella, then to the tibia via the patellar ligament. All right. Um, Muscles need both fuel and instructions. The femoral artery provides oxygen and nutrients to the quads, while the femoral nerve, emerging from the lumbar spine, controls muscles' contractions. The brain sends an electrical signal through the spinal cord, down the femoral nerve, and into the muscle. That causes the muscle fibers to contract by releasing calcium inside the muscles, a process called excitation contraction coupling. This communication must be fast. In elite athletes, for instance, muscle reaction times are often under 200 milliseconds. Now, muscles generate force, but tendons transmit that force to bones. The quadriceps tendon connects the muscles to the patella, which acts like a floating lever. Then the patellar ligament connects the patella to the tibia. When the quads contract, they pull on the tendon, straighten the knee, and move the leg. Without tendons, your muscles would be like engines with no wheels. All power, no motion. All right, now for the physics. The quads operate as a third class lever. Here's what that means: the fulcrum is the knee joint, the effort is applied by the quads via the tendon, and the load is the weight of the leg, and any external force like the ground during a jump. In a third class lever, the effort is between the fulcrum and the load. This setup sacrifices mechanical advantage but gains speed and range of motion, exactly what athletes need for quick, explosive leg movement. Now, just as a bonus, we can contrast that with a second class lever, like a wheelbarrow, where the load is between the fulcrum and the effort. Much better for heavy lifting, but not great for speed. The body trades raw lifting power for explosive movement. All right, now it's time for some calculations. So, let's calculate the torque the quads generate during movement. If the quads produce a force of 300 newtons and act 4 centimeters or 0.04 meters from the pivot, the knee joint, then the torque would be, well, torque equals F times R, and so it would be 300 newtons times the 0.04 meters, which is 12 newton meters. Torque is what causes rotational motion around joints. It's like turning a wrench, where the distance from the pivot changes the amount of rotation. For elite athletes, for instance, peak quadriceps forces can be over 1,000 newtons, creating torques above 50 newton meters. All right, um, now for work and energy output. So work is defined as force times distance. So if your quads extend your lower leg zero point 0.3 meters while applying 300 newtons of force, then since work is force times distance, the work would be 300 newtons times zero point 0.3 meters, which is 90 joules. That's 90 joules of energy just to kick your leg out once. Now imagine that in the context of sprinting or jumping, where both legs are involved and movements are repeated rapidly, we're talking hundreds or even thousands of joules per second, aka power. So, just as a bonus, we could actually calculate the power. Since power is work over time, then if this 90 joules is done in just zero point 0.2 seconds, for instance, then the power would be 90 joules divided by zero point 0.2 seconds, which is 450 watts. That's like a high power blender in your leg. All right, now let's talk moment of inertia, which is like rotational mass. It tells us how hard it is to rotate the leg. For a swinging leg, we use I equals 1/3 mr squared. Now, if the lower leg weighs, say, 4 kilograms and its center of mass is 25 centimeters from the knee, then the moment of inertia would be 1/3 times 4 kilograms times 0.25 centimeters or 0.25 meters squared, um, which equals 0.083 kilograms meters squared. Now, notice that the lower the moment of inertia, the faster you can swing your legs. Sprinters and jumpers often have strong but lean legs, not just for muscle, but to reduce inertia. All right, now for the vertical jump. This is a perfect example of explosive leg power. During a jump, the quads fire rapidly to extend the knee, while other muscles like the glutes and the calves assist. The entire lower body becomes a spring, pushing against the ground. Now, this motion would require fast torque generation, high energy output, short ground contact time, and an efficient kinetic to potential energy transfer. And now I have a video here of me demonstrating. It's just a slow. So, yeah, um, in order to achieve this type of movement, I would have to be generating a lot. I have to be outputting a lot of energy. And my quadriceps would have to be, well, doing a lot of work. Yeah. All right. Now it's time to analyze the physics of the jump. Um, Using all of the information we've learned, we can actually calculate some things. For instance, suppose an athlete exerts 1,000 newtons of force over a zero point 0.5 meter push. The work, since work is force times distance, the work would be 1,000 newtons times zero point 0.5 meters, which is 500 joules. Now, what you have to understand is that this work turns into gravitational potential energy. And since potential energy is defined as the mass times the gravitational constant times the height, we can rearrange the equation to solve for the height, um, which would result in the height equals potential energy over mass times gravity, um, which in this instance would equal 500 joules over 70 kilograms. I'm just using 70 as an example of potential mass of an individual. So 500 joules over 70 kilograms times 9.8 meters per second squared, which is roughly 0.73 meters. So that means that the athlete would jump around 73 centimeters. And that is actually elite level vertical. Um, we can also estimate, just as a bonus, we could also estimate the vertical velocity using energy. So we can find how fast the athlete is moving at takeoff using the kinetic energy formula. Um, so kinetic energy, as we know, equals 1/2 mv squared. The energy from the jump is 500 joules, and since that energy is the potential energy, we can set that equal to 1/2 mv squared, since kinetic energy is being converted to potential energy. So, assuming the athlete's mass is 70 kilograms, we could say 1/2 mv squared equals 500, and rearranging the formula by multiplying by 2 on both sides and dividing by the mass on both sides and then square rooting both sides, you'll get that the velocity equals 3.78 meters per second, roughly. So that means that the athlete leaves the ground at about 3.78 meters per second. All right. So, in conclusion, to wrap it all up, the quadriceps are an incredible example of biological design and physics working together. Their structure gives us explosive extension, their force output creates torque, and their lever setup trades strength for speed. Now, whether you're sprinting, jumping, or even just walking upstairs, the quads are key to every powerful lower body movement. So next time you land a dunk or leap for a spike, just remember it's physics that got you there. Now that is the end of my project and my presentation. I hope you guys enjoyed it. Thank you for watching. And yeah, just remember there's physics in every moment.